Good afternoon. Welcome to the first of our Hartwig lathe programming webinar series covering turning cycles. We're going to go through as many questions as we can, but with large attendance. We're going to try to keep it to an hour. So for the sake of time, we will follow up with an email with all questions and answers mid to late next week. Without further ado, Hartwig helps people in manufacturing control their destiny every day. This is something that all of our team truly does believe in and live every day, and that's why we're doing this presentation today. We are here to help you guys Our goal is to help everyone have a better understanding of how to run their machine and how to be more efficient. And that's what we're going to do today. So before we start talking about how to write a program, we need to talk about some of the codes associated in those programs. The first section of codes we're going to talk about are called preparatory G codes. So G17, G18, and G19 are a group of codes that we call plane selection. Typically, when you're programming a 2-axis lathe, you will be in the G18 mode, which tells the machine to calculate all of our arc commands in the plane of X and Z axes. G50 is a command we have to have in every single program, which is max RPM designation. It also has a zero shift function, which I would not recommend doing. And on the next slide, we will talk about how G50 needs to be used so that that zero shift doesn't happen when we intend to use it for max RPM. G90 and G91 are going to tell the machine in which method we intend to position. G90 is what we call absolute positioning, meaning every coordinate point of your part is going to be referenced from one datum position that's fixed. Typically for me, and in all of our examples we'll see today, that is from the front of the part to the back of the part. G91 is what's called incremental positioning mode. That means that we are going to move point to point. So wherever the tool is currently sitting, if we were to say Z-2, the machine is going to move 2 inches or millimeters in the negative direction from wherever it is sitting. And there are some benefits to using incremental. Most of the time, you will be programming a machine in absolute. G94 and G95 are our feed modes, whether we are in feed per minute or feed per revolution. All of our lathe programs today will be in feed per revolution mode, as we're just doing simple 2-axis turning work. And G96 and G97 are constant cutting speed on and off. We'll talk a little bit about what constant cutting speed is, but this is a great tool for turning and grooving. Anytime you are changing diameters and you would like to adjust your RPM, G96 constant cutting speed on is a great way to do this within a program easily. So as I said before, G50 has 2 main functions: maximum spindle speed setting and zero shift. For this reason, never put axis motion on your G50 line when you are using it for max RPM. This must be designated at the top of the program before you turn on the spindle, or an alarm will occur in the machine, and this will have to be commanded. G50S of some number will tell the machine when designating a speed in G97, or when calculating an RPM using constant cutting speed, do not exceed the S command. If you put an axis command on the G50 line, a zero shift will occur. This can cause a machine to crash, as if you put, say, your first coordinate point, G50 S of some speed and Z-5, the machine is going to shift the part datum 5 inches in the negative direction and reference that point for the continuation of the program. So again, we never want to put an axis motion on the G50 line. Constant cutting speed. G96 is constant cutting speed on. This is used to achieve a desired surface feet per minute. So if we command G96 S900, the machine will reference the active actual position of the x-axis, accounting for our tool offset, and adjust the RPM automatically to achieve 900 surface feet per minute traveling over the tooltip as the machine runs. G97 is constant cutting speed off. So now we are commanding a directed RPM. G97 S900 will turn the spindle on at 900 RPM in the designated direction. And the only time that RPM will change is when commanded to do so. Positioning G-codes. G0 is used for rapid positioning. That is going to tell the machine to move as fast as possible. And it is not going to take any defined path. So if you have an X and a Z on the same line with a rapid position, it may reach the X position before the Z position, meaning you need to be aware of objects that may be obstacles for the turret as it's rapiding into position. And that may determine whether you put an axis before, such as a Z move, then an X move to miss a tailstock or a center or some kind of support. G1 is linear positioning. This is going to be our feed in a straight line command. This could be an angle, direct point to point, or this could be a straight turn. G2 and G3 are going to define our arcs. There will be some additional definition we'll need to do for these that we'll talk about. And G40, 41, and 42 are how we are going to use nose radius compensation. And in a later slide, we'll discuss how to program nose radius compensation. G75 and 76 historically have been an option on older controls, but on the P300 control, it is a standard. This is automatic chamfering and automatic corner rounding. It is a great function to be able to break a sharp corner within the program, do some deburring while you're turning the part, and save the operator some additional operations when the part comes off the machine. Defining arc commands. There are two ways we define an arc command. First, we have to give it a G2 and a G3 to tell whether we are going to use a clockwise arc or a counterclockwise arc. Now, the way you know the direction that the arc is going to be defined is by looking at the part and referencing the direction the tool is traveling, whether that is clockwise or counterclockwise. It's always based on the direction that the tool is traveling. Then we need to tell the machine the end point of the arc in both X and Z in this case when we're in the G18 coordinate plane. We then give the machine an L for the radius of the arc, or we use I and K to define the center point of the arc. And we'll see an example of that in the next slide. The simplest way to define an arc on an Okuma lathe is with an L value. L is just the radius of the arc, and then F will set the feed rate. However, in some cases, it's necessary to use I and K to define the center of the arc if the machine is giving an arc calculation error with the radius. In this case, whether you are in G90 or G91 mode does not matter. I and K are the incremental distance from the start point of the arc to the center of the arc. As we see here in the figure on the left, this is going to have a K value of the difference in the Z axis from the center to the start point, and an I value of the distance from the center to the X position of the start point. tool nose radius compensation. Nose radius compensation is once again calculated in the direction the tool travels. So in our example below, we are programming from the front of the part to the back of the part, and that is the direction our tool is traveling. We can see that G42 is used for tool nose compensation right, which is going to be my turning tool for this part. G41 is going to be my tool nose compensation left, which is my boring bar on this part. As the way the tool travels from front to back, we need the nose radius to be on the left side of the path. And G40 is used to cancel tool nose radius compensation. When using roughing cycles and finishing cycles that we're going to talk about later, you must cancel tool nose radius compensation before ending the shape designation, or the machine will alarm. If not using the turning cycles we'll discuss, lap cycles, you must cancel tool nose radius compensation before ending the program, or the machine will also alarm. Automatic chamfering. This is a function, like I said before, that is very nice for deburring a part in process, and it will calculate the start and end point of your chamfer automatically. What the programmer must do then is define an intersection point. So for instance, in our example here, the tool is sitting on the face of the part at point A. We have a G1 to point C with a G75 to tell the machine automatic chamfering, and an L value of 5 millimeters. Now, this example uses -5 millimeters. On older controls, when it was an option, positive and negative was necessary to tell the machine which direction the tool is traveling to help with calculation. On the newer P300 controls, positive and negative is not necessary, but will not alarm your machine out. The machine will calculate the direction on its own based on the next point. So we have a chamfer of 5 and a feed. On the next line, we would have a Z minus to point E, and automatic chamfering will calculate points B and D within the process and cut that chamfer just based on defining points A and E. Automatic corner rounding programs exactly the same as automatic chamfering, which we just discussed, but it's a G76 command. And the L value defines the radius size instead of a chamfer size. Now we need to talk about some of the M codes associated with programming in Okuma. M0 is program stop. This is going to stop the machine every time you run the program. Say you need a part flip of some kind. This can be a good way to pause the program, flip the part, reclamp, and continue the program on without having to select two different programs. Versus M1, which is an optional stop. This I use at the end of every single tool, which allows us to toggle a panel button called optional stop on or off based on if I'm running a part for the first time and I want to check, say, my roughing feature before I finish the feature, or I want to check a tool because it sounds like it's been cutting a little rough whenever it's done. I can turn on optional stop. The machine will run that tool up to my M1, pause. I can do what I need to do, close the door, cycle start, and resume the program without having to hit reset and do a restart. M2 is how you end programs in the Okuma. And M3, 4, and 5 are going to be our spindle commands. M8 will toggle coolant on, and 9 will toggle it off. We can orient the spindle with M19. M30 is also acceptable for ending the program in an Okuma, But what you'll see more often than not on an M code table for the Okuma machine tool, M30 will be called end of tape. M41 and 42 will define our gear range. And then we can command our tailstock advance and retract with M55 and 56. If you have an NC tailstock, a full programmable NC tailstock, M847 will rapid the tailstock to the limit of the W axis so that you can load a new part, and then using M55 we can bring that tailstock back to the retract point we want to approach the part from. The Okuma machine tools use a 6-digit tool change command. These are used for tool nose radius compensation, the turret station number, and the tool offset number. So if I want to call up tool 1 and use nose radius compensation, I need 6 digits. T01, telling the control, reference tool offset 1 for my tool nose radius compensation value. Then 01 again, telling the machine, index the turret to station number 1. And lastly, 01, telling the machine, go reference tool length offset number 1 to compensate for the X and Z axis of my tool. However, as we note at the bottom, when using a drill or a tap or a grooving tool that doesn't have a radius, we only need 4 digits. Since the first two are tool nose radius compensation, when not using G41 or G42, that can be 00. So we could call up T0303 and not need the first 2 digits when not using nose radius compensation. Now we're going to talk about lap cycles. Before we get into lap cycles, do we have any questions, Joe, about what we've covered so far?
We do have a few questions, Ricky. Someone asked on auto chamfer, why is it only going back 5 millimeters in Z and 10 millimeters in X? And that was a few slides ago, and they were asking, should it be 5 and 5?
Yeah, that's a good question. So the reason we are going 5 millimeters in Z and 10 millimeters in X is because the Okuma control programs in diameter. So any command we give in X-axis is a diameter value, whereas the Z-axis is going to be the size of the chamfer. So when we come back, when we cut a 5 millimeter chamfer, we can go to Z minus 5, but in X, we need to command double the desired size of our chamfer so that the machine doesn't cut it undersize. Do we have another question, Joe?
That is all the questions we have for now.
Perfect.
Oh, wait, hold on. Could you explain a basic bar turning can cycle and how it's formatted? I think we're getting ready to get into that.
Yep, that's what we're just getting ready to start. So I will move into lap cycles. These are some of the commands that will be necessary for programming a lathe auto programming cycle, or as somebody in the chat just called it, a bar turning cycle. G80 is going to be our end of shape command. So once we're done defining the shape of our part to turn on a bar, we will use G80. G81 and G82 command the machine which direction to turn in. So a G81 roughing shape would be a long turning or a Z-axis turning motion, versus a G82 tells the machine to do a face roughing operation in the X-axis. G85 is a rough turning or rough boring cycle, and we will define within that G85 command a depth of cut, stock to leave for finishing, the starting point of our shape, and a feed rate for roughing. Then a G87 is going to be our finish turning and boring cycle. It's important to note on the Okuma control, we must define the feed rate for a finishing cycle within the actual shape definition. The machine will not recognize a feed rate on the G87 line for finishing. So let's look at a sample program for how to rough out this part. Pretty simple OD part. We've got a couple radius and some straight turns. Our program 0 is the front of the part, and we're gripping on a 2 1/4 diameter, only turning back 2 inches. So I like to start every program with a heading. Typically the first line will be if it's a family of parts or the name of the company, whatever makes sense to that job. The next line will be a part number. In this case, we're programming part LD6 from the lathe programming manual used here in the office to teach classes. And I like to put the programmer's name. In this case, the programmer is myself. This gives accountability to the person who wrote the program. And if the person who wrote the program is different than the operator, it gives the operator a resource to go back to. Hey, I'm having a problem with this program, or engineering came down with a print change and I'd like you to help me make that adjustment. It can be really nice to just know who that person is without having to track down who wrote that program. The date of the previous revision to the program and the rev level of the print, so that the operator knows if they get a print come down for a repeat job, say it's Rev B, well, this program is Rev A. Maybe we need to get the programmer named above involved and find out if there's any changes. Then I like to put a tools list. Within my tools list, I have on the left the restart point in the program to get to that tool if, say, I need to rerun the finish pass and I don't want to run the whole program. And then I have details about the tool. So tool 1 is going to be a rough turning tool for the OD 80 degree. So we're using a CNMG insert. Tool 2 is going to be a finish turning tool with a 35 degree included angle. Then I have my graphics commands. Clear will clear the graphics window, and draw will start drawing trace. And if I have defined my graphics, it will also draw my part and tools. The next line is going to be a safety line. This line is going to put the machine in the condition I anticipate that it would be in before starting to run the program, because we don't know what types of commands have been left in the machine. There are commands called modal commands, which once they have been commanded, they stay active until another command in that category pushes it out of the machine. So in this case, I'm telling the machine G0, I anticipate it to be in rapid motion for any moves going forward. G18, I'm saying I want to calculate all of the arcs in the XZ coordinate plane. G40, just in case I may have hit reset in the middle of a roughing cycle and my tool radius compensation was not canceled, cancel tool radius compensation to prevent any alarms. G80, again, if I hit reset in the middle of any roughing cycles, I want to make sure those shapes are canceled and I'm starting fresh. G90 to tell the machine to be in absolute positioning mode. In G95, I intend to program INFEED per revolution. Then we have our max RPM. So G50 tells the machine I'm going to designate a max RPM. And in this case, my S tells me that is going to be 3000 RPM. Then we have a restart point, NAT1, which is not specifically NAT1 for any reason other than N tells the machine a sequence number or name is about to be defined, AT for A turret, 1 for tool 1. You could make these anything that makes sense to you. This is just how I'm defining them. And this is also how it will come out of IGF for anybody who uses conversational programming. Then some details about what's going to happen in this operation. So this tool is going to rough face and rough turn our part. It's an 80-degree included angle insert with a 32 thousandths nose radius. This information would tell me that when the machine was set up, someone should have placed the number 32 thousandths for nose radius compensation in the X and Z fields. G0X20 Z20 is a safe move that I like to use at the beginning of my tool block. This tells the machine to rapid to the X limit and the Z limit. For those customers with larger machines, you may want to make this X50, Z50, X100, Z100. What we are trying to do is put a number larger than the travel and let the machine rapid to the limit. That is possible in an Okuma as long as you are not in a feed move. It must be a rapid move to put a larger number than travel and get to the limit. T010101. So we're activating tool number 1's tool nose radius compensation and tool length offset compensation offset values and indexing to turret station 1. The machine must be at the limit to make the index. G97 S1403 M4. So we're turning on the spindle to 1403 RPM in the counterclockwise direction, meaning my insert is going to be facing up and my tool nose is facing to the left to get ready to turn my part. The reason I'm using the speed 1403 is because at the diameter I am turning on constant cutting speed. This is what the calculated RPM would be. It'll save a couple seconds of cycle time so that the spindle doesn't have to ramp up or down when G96 is commanded. Now we are going to rapid the tool to what I call a clearance position or a standoff position. X of 2" 450, Z of 100 thou. So we're going to be 100 thou away in the radius of the part and 100 thou away off the end of the part while turning coolant on. Then we're going to activate constant cutting speed to get ready to face and turn our part. We're going to rapid to Z of 3 thousandths off of the end of our part so that we leave some stock for finishing. G1 X minus 65 thousandths, feed rate of 10 thousandths per rev. The reason I'm going past center by 65 thousandths is, again, the Okuma program's in diameter, and I need to pass up center to face off the part flat completely, which means I need to go past center by double my nose radius in X to do so. I rounded that up to 65 from 64. Rapid to 100 thousandths away from the end of the part again, and rapid to X of 2 1/4. The important thing to note here is I am rapiding to the exact stock diameter because we're now going to define our bar turning or our rough turning cycle. When we do that, the rough turning cycle is going to reference the current position of the tool and take my first depth of cut step down from this point. So if we returned back to our clearance position, we would have a very light depth of cut or cut air on our first pass. And we don't want to cut air or rub the part. We want to take a full depth of cut on the first pass. So I always rapid to the bar diameter. Now we have our bar turning cycle for roughing line. G85 tells the machine we're using a roughing cycle. NTUR1, again, is just a sequence name. That is what I'm calling the first line of my roughing cycle designated shape. N for sequence name, TUR for turning, 1 for turning 1. U of 30 thousandths tells the machine I am going to leave 30 thousandths in the X axis or on the diameter of the part. W of 3 thousandths tells the machine I'm going to leave 3 thousandths on all shoulders or in the Z axis. D of 150 thousandths is a depth of cut of 150 thousandths in diameter. So my insert will only be 75 thousandths engaged into the workpiece, and a feed rate of 15 thousandths per rev. Our next line, I'm telling the machine, this is end turn 1. This is the start of my shape. In G81, I'm telling the machine, what direction do I want to rough this? Do I want to rough this in the Z-axis? Or do I want to rough this in the X-axis, or what I call face roughing? In this case, we're going to rough this in the Z-axis, longitudinally. Then I'm rapiding to a point below my start diameter to get ready to put a chamfer on the front of the part, and about 30 thousandths away, while turning on tool nose radius compensation right. Then feeding to Z0, or the face of my part, and this F of 8 thousandths per rev is going to be the feed rate for my finish pass. We have a G75 for automatic chamfering on. We're going to feed up to X of 375, or 3/8 of an inch, with a 15 thousandths chamfer on the front of the part to break the edge. And we're going to turn back Z minus a 1/4 inch. Then we have a radius on the part. G2 is going to be a clockwise radius in the direction my tool is traveling. And again, we have to double the radius to get our X value. So the end point of my radius is going to be 875 thousandths for a 1/4 inch radius. And our coordinate point from the front of the part is Z minus a 1/2 inch. Then we have a straight turn back to minus 1 inch, 125 thousandths. And a straight turn up in X to 1 inch, 175, preparing to cut the next radius. We found that point because the print dimensioned the shoulder at 1 inch, 375 with a radius of 100 thousandths. So this time I subtracted double my radius to get the start point of the radius. We now have a G3. This is going to be a counterclockwise arc to our end point, which was our print defined position of 1 inch, 375, and our Z minus 1 inch, 225, because we're going back 100 thousandths, or the radius, farther from the shoulder, and then an L to define my 100 thousandths radius. We have a straight turn, Z minus 1 3/4. Another arc, this time going to X of 1 inch, 875, which is double my radius higher than my current X position. Z minus 2 inches, which is the size of my radius farther back in Z, with a radius of a 1/4 inch. A straight turn up in X, and I'm using a G75 automatic chamfering again to put a corner break on the part so that there's no deburring when the part comes off the machine. And to define the second point of my intersection, we have a Z minus 2.3. The reason I'm going 50 thou past the shoulder is to give the machine room to calculate the endpoint of the chamfer and cut a chamfer on that corner. If I just define Z minus 2 1/4, the machine can't move far enough back to calculate the 15 thousandths chamfer. Then we're coming off the part and canceling tool nose radius compensation back to our clearance point in X. In G80 cancels my shape. I'm done. This is the end of my shape designation. We change the spindle RPM back to G97. I like to do this before I rapid the turret back to the limit, because if it stays in constant cutting speed, the machine will slow the spindle down to a point where it's almost at a complete stop, which can be really hard in the brake over time and can also cost you cycle time. So we'll go back to G97, and the S3000 is going to be the RPM my finishing tool will start constant cutting speed at, so that I don't have spindle ramp time in between. Rapid the turret to the X limit and Z limit to prepare for the next tool, and turn the coolant off. Never index your turret with the coolant currently running. Always shut coolant off before changing tools. Then we have an optional stop. So at this point, if I'm running the part for the first time, I'm probably going to pause, open the door, mic some diameters, measure some lengths, and make some offsets to my roughing tool depending on what I expected the dimensions to be before I continue on finishing the part. Then we continue on to our finishing tool. We have our restart point, N, A turret, number 2. And we have some details about our finishing tool. We're going to finish the face of the part. We're going to turn the OD of the part with a 35-degree, 15 thousandths corner radius tool. Again, I have a safe line here. It's not really necessary since I ended the last block with it, but I included it for the purposes of a simple part and program. T0202 tells the machine to activate tool nose radius compensation offset 2, index to tool number 2, and activate tool length offset number 2. Again, we're making sure the spindle is turned on and rapiding to a clearance point. This time I'm going to 100 thousandths away radially from my smallest diameter. Saves a lot of time so that I'm not facing air all the way down the part. Now I'm at double my 100 thousandths away in X positionally because again the machine programs in diameter. 100 thousandths off the end of the part and turn coolant on. Then we're going to turn constant cutting speed on to 900 surface feet per minute again. Rapid to Z0 this time because we want to finish the part to length. G1 X minus 30 thousandths this time because I want to go double my nose radius. Rapid to 100 thousandths off the end of my part. And I'm rapiding this time to the start point of my finish shape. Now we have our G87. This says I'm going to finish the part this time, starting from NTUR1. The control is then going to literally read this toolpath, including my finish feed rate, all the way down to G80, at which point it will return to this point in the program, but the tool will stay at my last point of my shape. We're going to turn off the spindle with M5, rapid to the limits of the machine and shut off coolant, and end the program. Now that we've walked through an example of this program, let's see it run in a simulation video. So we see our roughing cycle running. Our finishing tool comes in, faces off the part, finishes the shape, and our program ends. Do we have any questions about the program we just went through, Joe?
No questions exactly on the program unless one just came in. Okay, actually one did just come in. Why do you have to turn the coolant off to change tools? Just came in.
It's preferable to shut the coolant off whenever you change tools because otherwise the coolant will stay on and spray behind the turret as you index, which over time can get pretty oily and sticky and can cause issues later on down the road.
We had a question come in. Does the P300 control allow for multiple edge offset calls, i.e. turning 3 different diameters with one finish tool? And can I use one offset on each edge or diameter independently?
You could. You can define 2 offsets in the P300 control for one tool number. So if we have tool 1, edge 1, edge 1 can have 2 offsets, but tool 1 can have 12 edge positions. However, I'm not sure that would be the best way to go about programming a part. I would probably encourage you to, if you have 3 different diameters you need to turn and you want to adjust them differently, to do that within the program. But if you'd like, we could talk more about why you may want to do this offline outside of this webinar.
And then there was another question if you could actually see the part you were trying to machine, but I think we answered that whenever we ran the simulation there at the end of the program. Some more came in. Why do you have to specify a speed when you command an M5?
Simply, I've always gotten an alarm in the Okuma control if I command an M5 without an RPM. So I'm specifying a speed so that I don't get an alarm.
Can the stock and tools be defined in the program for the simulation?
On older controls, it is necessary to program the stock and tools within the program. On the P300 control, you go to Parameters, Optional Parameters Easy Op, and you have to change the parameter to tell the machine, I do not want to use the P300 graphics. I want to define them within the program, and that will work. Standard on the P300 and from the factory, you will have under your one spindle setup tab your stock definition, and in tool data you will define your tool shape unless you change that parameter.
Okay, we had another one come in. Why did some of your L's use negative and some of your L's were positive?
I used the positive and negative showing the definition of direction on the older controls. But as I said, on the P300 control, it's not necessary to do that anymore. You can just give a positive L for the size of the chamfer radius. On older controls, the positive or negative tells the machine whether we're cutting that chamfer radius in the X or Z negative direction or the X or Z positive direction based on the direction the tool is traveling. Okay. So our next sample program is going to be very similar. This one is going to be a boring program. So the part of the program I've removed for simplicity's sake is drilling. There's a drilling portion above this that we'll talk about later. I just want to focus on the rough and finish turning of this part. So when I get to my G85 cycle, which you see highlighted in yellow, I have all of the same information as I would for a rough turning. I have a G85, end bore 1, leave 30,000 stock in X, leave 3,000 stock in Z, take a depth of cut of 1/8 inch with a roughing feed rate of 10 thousandths per rev. But at the end of the program, when we use our G87, the machine will finish bore the part, and the boring bar will wait at the final Z position inside the hole until commanded out of the hole. You must put a G0, Z.1, or a feed move of some kind out of the hole before rapiding to the limit. Otherwise, your boring bar will rapid into the wall of the part and break. see how this one runs. Now let's talk about OD grooving. An OD grooving cycle is going to have an X and Z coordinate point for targets. I is the shift amount in the X-axis direction. Typically that's going to be 0 for an OD grooving cycle. K is going to be the shift amount in the Z-axis direction. This is going to be the width of our grooving tool. D and L are going to work together to define the depth of cut. D is going to be my peck amount. L is going to be the total incremental distance to travel in my peck amount increments before fully retracting out of the groove to clear chips out of the way. E is going to be a dwell for the grooving tool at the bottom to get full cleanup. Typically I use a half a second or a second. And then we need a secondary tool offset number for the opposite edge of the grooving tool so that the machine knows how wide the grooving tool is. DA is optional. That is to change the default retract amount from 1 millimeter to a larger or smaller number for your D-PEC. So this is a sample OD grooving program. We're using a G73 cycle. The groove is 3.5 inches in diameter, which is our X. Our end point of the groove is Z-3. But the grooving tool started at Z-2.25 because we're using a 1/4 inch wide grooving tool. I had to go a 1/4 inch past my start point. Stepping over in Z to cut a wide groove, I'm using 75% of the width of my tool, or K of 3/16. We have a depth of cut of a 1/4 inch with 1 millimeter retract, and an incremental travel distance of a 1/2 inch before retracting out of the groove, with a dwell of 1 second to get a full round groove. 3 thousandths per rev is my feed rate, and my secondary tool offset is 23 so that the control can calculate the width of my insert. So we saw our roughing tool run again. This is going to be our finishing tool using a G87. And here comes my grooving tool, pecking a 1/4 inch at a time, retracting every 1/2 inch of distance traveled to clear chips, and dwelling for a second at the bottom to get a full round groove. Something you may choose to do is use this cycle to rough out a groove, and then maybe come in with some manual code using G1 to finish the groove later if you need a higher surface finish. G74 is what's called a... Yes, sir.
We have a few questions I think we should get to first.
For time's sake, let's finish going through grooving, okay, and then we can answer questions.
All right.
G74 is what we call a face grooving cycle, or can also be used as a drilling cycle. This uses the exact same commands as a G73, but this time your step over of your grooving tool is going to be in I, as you would be stepping over in X. So to drill a hole, my I would be 0, which tells the control I don't want to step out and cut a wider groove. I just want to drill through the center with X being 0 and wrap it out of the hole. We'll also talk about tapping cycles. When tapping in an Okuma, It's important to note G77 is a definition of tapping mode, which is controlled by a parameter. So this can be float, standard from the factory, and it will be float until you buy the lathe spindle sync tapping option, which then gives you G107 and G108 cycles. But once you purchase that option, you get this parameter page, as I show in the bottom right corner, and you can change G77 from float to concurrent. So if you do not have lathe spindle sync tapping, you must use a spring-loaded collet or some kind of float tapping mechanism when tapping with the lathe spindle of an Okuma. For a tapping cycle, we have an X coordinate point, which is going to be 0, Z for the depth of our hole, K will be a shift. So if you have a 1/2 inch counter bore, you can shift a 1/2 inch from your clearance point to save time. It'll rapid to the bottom of the counter bore, tap in, tap out, wrap it out of the counter bore, and sit at your clearance point. And then feed rate is going to be the pitch of your tap. So in this example, we have a G74 for our drilling cycle at X0. At Z minus 1 inch minus our drill point of 62 thousandths to get to 1 inch 62 deep, with an I of 0 to drill, pecking a 1/2 inch with 1 millimeter retract, incrementally moving 1.5 inches total, with a feed rate of 3 thousandths per rev. Then we have a synchronized tapping right hand tap cycle at X0 to 600 thousandths deep. We're going to tap in 1 time and tap out 1 time, so my D and L's are large numbers, and our feed rate is pitch. The pitch of our tap is 1 divided by the number of threads per inch, which I'm letting the control do the math on. On older machines, you may need to put F equals in order to get the math to work out. So now we see our tap coming in. And tapping out. Okay, if we have any questions for grooving, let's go ahead and go over those now, Joe.
I think one of them goes back a little further than that. Why do you have to specify the finish cycle with a G87? Why can't you use line-by-line programming like finish subprogram? And I think I think what he's asking there is, why do we have to use the G87? And we don't have to. I think that's more of a convenience thing. You can probably speak to that a little more clearly.
Yeah, you don't have to use G87 to finish a part. I'm simply showing how to program with lap cycles, and G87 is the lathe auto programming or lap cycle for finishing. If you prefer to just program the entire part line by line, you can absolutely do that. There's nothing wrong with that. I'm just showing how to use the machine's function in this example.
Then another question we have is, will these slides be available after the presentation?
After the presentation, there will be a follow-up email tomorrow morning with a recording of the presentation. You will also get a PDF of these slides in the presentation and a survey that we would like you to fill out, letting us know how we did with this class. So now let's talk about threading cycles. G71 is a threading cycle that, given these pieces of information, will rough and finish a thread. So our X dimension is going to be the finish diameter of our thread. For an OD thread, that is the minor diameter. I think my computer's dying. For a ID thread, that is the major diameter. Then we have a Z coordinate, which is the end of the thread. A, if we have a taper angle, such as a pipe thread. B is going to be the included angle of our thread. So for a standard, that's going to be 60 degrees. For an Acme, that would be 29.5 degrees. D is depth of cut in the first thread cutting cycle. U is finishing allowance. So typically I will use a U of 5/10. H is thread height expressed as a diameter. L is chamfering distance if M23 is used. I typically program threads with M22 so that I get full depth thread all the way across the part. F is your feed rate, which is going to be the pitch, or F is your number of threads per inch, or F is going to be the number of leads when J is the number of threads per inch. So you can either have, say, for a 13 thread per inch thread, you could have F of 1 lead, J of 13, or you could have F of 1 divided by 13, J of 1. Some M codes for thread cutting pattern, and a Q for the number of leads. M32 tells the machine to thread along the front face of the insert. M33 tells the machine to thread in a zigzag pattern each pass. And M34 tells it to thread on the right face. We then also have to tell the machine an INFEED pattern. So M73 says to take our depth of cut each pass until it gets D depth of cut away from the bottom of the thread, and then divide our depth of cut in half, and then by 4, and then by 8, and then by 8 again, and then take our U if defined. M74 says just take the depth of cut until you reach U stock away, and then take the U. If there's no U defined, it just keeps taking D depth of cut until the thread's cut completely. M75 gets a little more complicated and depends on whether you use M32 or M34 or M33. So if you want to use INFEED patterns 3 and 4, I would recommend you go to the P300L programming manual and read up on those, as they get very complex in the math behind them. I typically like to use M73 as a standard for cutting threads. G33 is a similar cycle, but this is just one pass of a thread. This is not going to rough out your thread. And C is now used for your number of leads. You're going to be C0 to match your first lead, or C180 if you have 2, so on and so forth. And this is just going to take one pass of a thread. For instance, in finishing, like I'm going to do in the sample. So in this sample, I'm using G71 to cut the thread with chamfering turned off, zigzag threading with a M73 INFEED pattern number 1, then finish turning over the part again to deburr the thread, then using G33 to run the threading insert back through. So we rough out the part, finish the part. Our G71 cycle is threading the part now. Finish, and then one last time through at C0 to finish the thread. Are there any last minute questions, Joe?
None that I see.
All right. Well, we thank you guys for joining us for this session. I apologize for the technical difficulties the first time. Next time we do this, hopefully we have it worked out a little more. This is the first time we've attempted doing a Teams training session. As I said, you will get a follow-up email tomorrow from us that will have a PDF of the presentation, as well as a recording of today's presentation and a survey. Please fill out the survey and email it back to us. That'll let us know what we need to change for next time, or ways that we can improve, or maybe I can improve on presenting this in such a way that people would like to hear it. As well, next week, I will get together a list of all the questions that were asked today with the answers, and we will include that in email to everyone that attended. Thank you guys for joining us, and enjoy the rest of your week.